Section 3.2, Rules of Differentiation. So in this section, we'll learn some rules and formulas for derivatives so that we don't have to take that tedious limit every time. So in the last section, we were using limits to find the derivative of a function. Here we're going to come up with some rules that make it faster. So some of them intuitive, some of them not so intuitive, but we'll come up with lots of rules here and then lots of examples to see how they work. So the first question, what is the slope of any constant function? So if f of x is equal to c, where c is a constant, what is its derivative? Well, remember the derivative is slope. So f prime of x, in the case of x, f of x being a constant, should be the slope of a horizontal line, and the slope of a horizontal line is 0. So the constant rule says the derivative of a constant is always the number 0. And so again, if f of x is equal to c, then that would imply that f prime of x was equal to 0 in symbols. Some other ways we could say that, if you had a constant and you took the prime of that, that would be 0. You could also say if you took the derivative with respect to x of some constant, you would get 0. So that's kind of all the different notations. But because a y equals c line is horizontal and the slope of horizontal lines is 0, the derivative of a constant function is always 0. All right, so that just comes up a lot, so we need to kind of have that formally written down. One that comes up a lot also and is not nearly as obvious is the power rule. The power rule says to find the derivative of x to some power n, what you want to do is multiply by the original exponent n and then subtract 1 from n to get the new exponent. So what does that look like in symbols? If f of x is equal to x to some power n, then that implies that the derivative of f of x is equal to n times x to the n minus 1. So you see that, let's look at the highlighting here. So they said to multiply by the original value of x, so that was doing this piece. And then they said to subtract 1 from the original exponent, and that's what we're doing right there. So when you want to take the derivative of x to some power, you bring the power down out front as a multiplier, and you subtract 1 from the exponent that was to get your new exponent. So with those two rules in hand, let's go ahead and find some derivatives. So if f of x is equal to -9, then what is f prime of x? Well, this is a constant function, so the derivative would be 0. If f of x is equal to x to the 4th, then what's the derivative? So we would bring down the 4, start the notation off a little bit better. We're switching from the original function to the derivative, so I should say that. So this was the original function, but now we're taking the derivative. So I don't put an equal sign there, I put an arrow to distinguish that I'm transitioning from one type to the other. I had the original function, now I'm working on the derivative function. So to do that, I bring that 4 down to the front as a multiplier, and I subtract 1 from the old exponent, which was a 4. So now it's a 3. If you want to apply that to something like f of x equals the square root of x, then there's something that you need to know about square roots, and that is that they can be written as a fractional power. So the square root of x is the same as x to the 1/2. In fact, fun fact over here on the side, the nth root of x is equal to x to the 1/n. So if you have any type of root, you could always rewrite that as x to a power, and that would allow you to apply the power rule for derivatives. So I didn't write derivative yet because all I've done so far is write the square root a different way. So I still used an equal sign because the square root of x is equal to x to the 1/2 without taking any derivative. Now that I've written it as a power, I want to start taking the derivative. So now I'll write an arrow and the f prime of x. I'll take that old power down and I'll subtract 1 from it. So write that out, 1/2 minus 1. So we end up with 1/2 x to the minus 1/2. And it's not written here, but I'm going to add it. So find the derivative and simplify. That should be our default directions, find the derivative and simplify. And it's not considered simplified if it has a negative exponent. So I can get rid of that negative exponent by pushing that x down from the numerator to the denominator. We'll change the sign of its exponent, so now that's 1 over 2 times x to the 1/2. And since it didn't start off with a fractional exponent, but it started with a root, I'll change it back to that. So that's 1 over 2 times the square root of x. So there's our answer for that one. All right, looks like we're invading the space of the next problem, so we'll draw a little separation. All right, another similar situation, no root this time, but we have 1 over x cubed. So just like, let's go back here, just like I got rid of this negative exponent by pushing it down to the denominator, I can take that x to the third and pull it up to the numerator, and that will change its sign to x to the -3. That's not simplified, but to use the power rule, it has to just be x to a power. It can't be 1 over x to a power. So I'm going to rewrite it like this, and then I can take the derivative, and I can do that by bringing the power down and subtracting 1 from it, so -3 minus 1. So that ends up being -3 times x to the -4, which is -3 over x to the 4th. So moving it back down to the denominator to make the exponent positive, and that's considered simplified because we're getting rid of that negative exponent. All right, see if we can squeeze in this last one. The power rule does apply to decimal exponents as well. This one, there's no change that needs to be made. We can just jump right into the derivative. F prime of x will come from taking the power down out front as a multiplier, times x to 1.7 minus 1, which would be 0.7. So that one actually is nice and fast, one step, and we are done. So that is the answer, and that is simplified as far as we can go. All right, so there's a few quick examples. Hopefully you see the tremendous power in the power rule, no pun intended there. If you think about like trying to take the derivative of x to the 4th, so bringing our attention back up here, if you were to look at that one and use the x plus h method, you would have to do x plus h to the 4th and expand that and simplify. If you look at a question like C, if you're doing the limit method, because you have a square root, you end up having to multiply top and bottom of the fraction by a conjugate. We've seen before that if you have fractions and you do the quotient, like the slope quotient, you end up getting a complex fraction that needs to be simplified, which is messy. And I don't even know what we'd do with this one, right? This one would be an altogether new thing we'd have to figure out. But the power rule applies to all of them and makes them nice and fast. All right, as we turn the page, we're going to now start learning more rules. And by the way, you do need to memorize these rules to use them. And so you might get a little nervous as you see a lot of rules coming up, but I would argue it's better to memorize these rules than to have to use the limit definition to find derivatives for all these things. So the first one is the constant multiple rule. If c is a constant and f of x is differentiable, then so is c times that function. So if you take a differentiable function, multiply by a constant, it will still be differentiable. And the derivative, so dx is a notation we can use to ask for the derivative. The derivative of that constant times the function is just equal to the constant times the derivative of the function. So what that basically says is you can factor a constant out of the derivative process. Just pull that out front. And so I'll show you examples pretty soon where we do that, but that's the rule. We didn't prove the power rule. That one's a little bit messy to prove. You can look for a proof of that in the text if you're interested. I will go ahead and prove this one for you. It's not too bad to show. So let's try and find the derivative with respect to x of c times f of x. So we're going to use the limit definition. So the limit as h approaches 0 of c times f of x plus h minus c times f of x all over h. And then this works out pretty fast and easy. There's a c in the numerator in both factors, so I can factor that out in the numerator. And then I have f of x plus h minus f of x all over h. And then we had a rule in chapter 2 that said we could factor a constant out front of a limit, so I'll factor that c out to the front. And then what's left is the limit definition for the derivative of f of x. And since f of x, we're told up there, is differentiable, we know that limit exists and would be f prime of x, which is just a different way of writing c times d dx of f of x. So there's your proof of that one. We're not going to prove many of these. We're mostly just going to use them, but that one's fairly straightforward, so I thought I'd go ahead and show you a proof here or there. Let's get another rule in here that's going to help us. It's called the sum rule. If f of x and g of x are both differentiable, then so is the sum f plus g. And the way you take the derivative of a sum is you just take the derivative of each piece. So it's the derivative with respect to x of f of x plus the derivative with respect to x of g of x. So when you're taking the derivative of the sum, you can just break it into two pieces. You could also write that the derivative is f prime of x plus g prime of x if you prefer that notation. But either way, it's saying you can just take the derivative of each piece separately. All right, so how do these rules help us? Well, they help us with polynomials a lot because polynomials are made up of x to a power with multiple terms. You're adding stuff together. This first one, by the way, is not a polynomial because it has a negative exponent, but the rule still applies. So what we can do based on the new rules here, and I'll just kind of mention which rule I'm using as we go through, there's an addition here, so I can take the derivative of each of those two pieces separately. So the derivative of this one is going to come from just taking the derivative of the first piece, so x to the negative 4 prime plus the derivative of the second piece, so that constant 3 prime. But for the x to the negative 4, we can use the power rule. So that would be negative 4x to the negative 5. So I brought the exponent down to the front as a multiplier and subtracted 1 from the previous exponent. And then plus 0, because 3 is a constant, and the derivative of a constant is 0. And just like before, we're not going to just differentiate. We're going to differentiate and simplify. So we're going to get rid of that negative exponent and say that this is negative 4 over x to the 5th. When we move that x to the negative 5 down to the denominator, it changes the sign of the exponent, and now it's positive. All right, so there's that one. Now this next one is a polynomial. So if you were to do this with the limit definition, it would be very messy, especially because of the x to the 4th. But we can separate that into 3 different terms. So any rule that applies to the plus will also apply to the minus when you have that constant multiple rule up top, because minus 7x is the same as plus negative 7 times x. So whether it's addition or subtraction, you can just take each piece's derivative individually. And when each piece is a power, you can use the power rule, and any constants that are sitting out front can just be moved out of the front and dealt with later. So if I want to take the derivative, f prime of x, let's just go through this term by term. That 5 is a constant, can just sit out front. Then you do the derivative of x to the 4th, which is bring the 4 down, subtract 1 from the power, so the 4 becomes a 3. Kind of a messy 3, so let's clean that up. And then you move to the next term. The 3 just sits out front. Then you do the derivative of x squared with the power rule, so you bring down the 2 as a multiplier, times x to the power 1 less, so 2 minus 1 is now a 1. Then move on to the next one. The minus 7 is a constant, just sits out front. You take the derivative of the x, and that becomes bring the power down, 1 times x to the 1 minus 1, which is 0, and then plus the derivative of the constant, and then the derivative of the constant would be 0. So trying to clean this answer up, we end up with 20x to the third plus 6x minus 7. So let's go ahead and highlight that answer, but then I want to point out a couple things too. When you take, let's get a new color here. When you're dealing with a linear term like that minus 7x, you just end up with the minus 7, and that makes sense, because if you think of that piece all by itself, the line y equals negative 7x is a line with slope negative 7, so the derivative of that piece should just be the negative 7. Yes, you can do the power rule like I did here, but once you start to see the pattern, you get rid of those extra steps and just say if you're working on a linear piece, you just get the slope, which is just the coefficient. So if you do that, that'll speed up the process for you a little bit. All right, let's go ahead and move on to the last one. They want us to find the derivative, but then also what does this tell us about the graph of f of x, and then let's see if it's true on the TI-84. So we'll deal with all the words later. Let's just start off with the derivative. So f prime of x, we've got two terms here. So the first one is just a power rule. So you have the constant of negative out front is like a negative 1 out front. So we just treat it like a constant, leave it out front. We bring the 3 out front as a multiplier, subtract 1 from the power, so the 3 becomes a 2. Using what I just told you before, this next term right here is linear. So if you think of that as negative x, what's the slope of a line with y equals negative x as the equation? The slope would be negative 1, so the derivative of that piece is negative 1. Again, you can apply the power rule, but it's faster if you just think about it this way. So there's our derivative, negative 3x squared minus 1. So there's our find the derivative and simplify piece. So now what's this other business about? Well, let's do some extra work on this. If you take that f prime of negative x, you could factor a negative out front, and that would leave negative, we factored the negative out front, so it's not inside anymore. We'd have 3x squared plus 1. So what's important about that? Why are they asking us to discuss this further? Well, x squared is always going to be positive. When you multiply it by 3, it'll still be positive. It could be 0, but it's never going to be negative. And then when you add 1, it's positive. So this part in yellow, because it's 0 or bigger plus 1, is always going to be positive. And then that positive number gets multiplied by a negative. So one of the things that we should see about this derivative is that it is always negative. So if the derivative is negative, I would expect that the slopes of all tangent lines to the original function would be negative. And remember, a line with a negative slope is going down, and a tangent line is trying to tell you something about the steepness of the graph. So if every tangent line is going down for this graph, then probably the graph is always going down. So the speculation would be the graph is always decreasing. So the graph is always decreasing. All right, and then that's easy enough to check on the graphing calculator. So let's switch over there and see if we see a graph that's always decreasing. So we'll go to the y equals, we'll enter in that function. So the original function, negative x raised to the, what was the power, raised to the third, and then minus x. Then I'll hit graph. Looks like I have the standard window here, and then as we trace on this, we see that it is from left to right. This function is always going downward. Every tangent line is going to have a negative slope, and that ends up matching up with what we suspected would happen, that the graph is always going downward or decreasing from left to right. All right, on to the next page. All right, so we're just continuing on with those same directions from the previous page, which is to find derivatives and to simplify. So let's get started on this next one. Before we can find its derivative, I'm going to rewrite it a little bit, because remember, you can only apply the power rule if it's x to a power, or a constant times x to a power, but it can't be a constant divided by x to a power. So I'm going to leave the 1 as is, but I'm going to rewrite the 1 over x as x to the negative 1. And remember, the square root of x is x to the 1/2. So if I bring that x to the 1/2 up, that would become x to the negative 1/2. So I want to rewrite these as just a constant times x to a power, because then I can apply the power rule. So we have to do that rewriting first. Now we're going to switch to finding the derivative. So now we'll start applying the rule. So one term at a time. The first term is a constant, and then we'll use the power rule on the next two. So the derivative of the 1 is 0. For the next piece, we have a negative out front. Then we bring down the negative 1, and then x to the negative 1 minus 1, which would be negative 2. And then on the next one, we have the 2 out front, and then we bring down the negative 1/2, and then x to the negative 1/2 minus 1, which if you do the work on that will become negative 3/2. So the derivative is done. The rest is just simplifying. So let's go ahead and do that. So this would, the 0 would go away, the two negatives would make a positive, and we have positive x to the negative 2, so that would be 1 over x squared if I simplified it, moving the x down to the denominator to get rid of the negative exponent. On the next piece, these 2's would cancel, and a positive and a negative would make a negative, so we'll be subtracting. And then we have x to the negative 3/2, so I'll make that 1 over x to the positive 3/2 to switch that exponent back to positive. So there's our overall answer to that one. Both found the derivative and simplified. The key being that you can't take derivatives in this initial form. You have to go ahead and get those as an x to a power, but no division by x before you can use the power rule. If you start dividing by something with an x in it, you have to use something called the quotient rule, and that's coming, but we're not there yet. And by the way, it's messy, so when you can avoid it, you should try. Speaking of quotient rule, another rule we're going to find when we get the quotient rule is a product rule, and right here we have a product of two different functions. So what do you do when that happens? Well, you can wait for a future section to learn the product rule. And unfortunately, the product rule doesn't turn out just the derivative of one times the derivative of the next. It's not that simple. So right now we don't have the product rule, so we're going to have to work around it somehow. So instead of doing a product rule, we're just going to take the product. We're going to do a multiplication before we get started so that the multiplication goes away. So if you multiply, just doing the FOIL type of multiplication, x squared times 3 is 3x squared. X squared times 2x is 2x cubed. Negative x times 3 is minus 3x, and negative x times plus 2 is negative 2x squared. And then we have a couple like terms here and here, so we'll go ahead and combine those and put this in descending order at the same time. So 2x cubed, and then the 3x squared minus 2x squared is just plus x squared, and then minus 3x. You do all that and you feel like you've accomplished something, and you have. You've gotten this ready to take the derivative, but you have, in fact, not taken the derivative yet. So we'll transition with this arrow and say, okay, now we're going to start taking the derivative. So I changed the label from f of x to f prime of x. And now I just want to start showing you how to kind of speed this up a little bit. Instead of moving the 2 out of the way and bringing down the 3 as a multiplier, you can just think of when you bring down the 3, multiply with the 2. So I'm going to show you where I am. So I'm over here, and I'm going to bring that 3 down, but there's a 2 there already, so the 3 times 2 gives you a 6. And then you have the x to the power 1 fewer than it used to be. So it was a 3, so now it's a 2. On the next term, bring the 2 down, and now it's x to the first, but you don't need to write the 1. On the last term, negative 3x, that's linear. What's the slope of a line? Y equals negative 3x, it's negative 3. So that would be the derivative of that term. And there's our overall derivative. So very easy, I think, actually, to take the derivative of this using the power rule, but you have to get rid of the multiplication first. All right, so very similar idea as we go down to this next one. This one has division in it, and we can't use the power rule on the individual 3 pieces when the derivative is there. So somehow we have to get rid of that derivative. So what's our pathway to get that done? Well, we're going to do a couple things. One, we're going to split this up into two fractions. And you can do that because remember, if two things have a common denominator, you can add them together by add them or subtract them by, in this case, subtracting the numerators and keeping the common denominator. So if you worked this way, you'd say the two x's are a common denominator, so you subtract, and in the top you get that square root of x minus x back. So those two are equal to each other, but we don't want to combine them. We want to keep them split. And then we want to simplify. So we have x to the 1/2 over x, and then minus just 1 because x over itself. And when you have a power divided by another power, you subtract the exponent. So the exponent that's unwritten there is a 1. So x to the 1/2 minus 1 becomes x to the negative 1/2, and then just minus 1. Again, I've just done a lot of work, and I feel like I want to box this or something that it seems like I should be done. All I've done so far is simplify the function. Now I'm going to take the derivative. So now we're transitioning from simplifying the function to taking the derivative. And we're going to take that derivative by taking this piece and using the power rule. So bring the negative 1/2 to the front, x to the negative 1/2 minus 1, which would be negative 3/2. The next piece is just a constant, and the derivative of a constant is 0. So you could write minus 0 or plus 0. I'll write minus 0 just because there was a negative there already, but that's just going to go away. And then we just need to simplify. So negative 1 I'll put up top. The 2 is in the denominator, and that x to the negative 3/2 can become x to the positive 3/2 if I move that to the denominator. And then, of course, the minus 0 just goes away. So there's our overall and simplified answer to this question. All right, let's have a look at another one. And now we'll kind of make a return to tangent lines too. So find the equation of the tangent line to y equals x to the 4th plus 2x squared minus 1 at the point 1, 2. So first thing you need to do is find the slope of that tangent line, and the slope of a tangent line comes from the derivative. So y prime or dy dx, if you want, those are different notations for taking the derivative here. I'm not using f prime of x because there was no function notation given to me, but I can still apply the power rule just the same and the sum rule just the same. So I have three different terms. I'll do each of those individually. The first one has a derivative of 4x to the 3rd. The next one is 4x to the 1st, and the third piece has a derivative of 0. So I'll skip writing the 0. All right, so how do I get the slope of the tangent line? Well, I plug the x value right there into the derivative. So that would be 4 times 1 cubed plus 4 times 1. That ends up just being 4 plus 4. So we get a slope of 8. So now we want to use y minus y0 equals m times x minus x0 to come up with the equation of the tangent line. And this right here is going to be our x0, y0. So this becomes y minus 2 equals 8 times x minus 1. So there's the equation of the tangent line. We'll go ahead and put it into slope-intercept form also. That'll help us graph it if we wanted to do that, and I kind of do want to do that this time. So y minus 2 equals, do the distributive property, so 8x minus 8, add 2 to both sides, and we get y equals 8x minus 6. So there's the answer to the question, and we are done with this problem now. But I am going to go ahead and graph it on the graphing calculator. And the reason I want to do that is we didn't prove the power rule, but we just used it to find this tangent line. So if we go look at the graph of the original function, and then we graph this line, and it looks at the point 1, 2, this is a good looking tangent line. That's kind of evidence that the power rule that I showed you works, even if it's not a proof. So let's go ahead and switch over to the calculator and take a look at that. So we'll go into the y equals, clear out our last function, put in the new one. So we have x raised to the fourth plus 2x squared minus 1. And then the equation that we came up with for our tangent line was 8x minus 6. And then we'll graph both of those. And we want to really focus in at the point 1, 2. So let's zoom in. So the point 1, 2, get as close as I can to that, right around there. So that's supposed to be the point of tangency, and it sure looks like the red line, which is supposed to be our tangent line, is coming in and touching at that point, and it also looks like the two are blending together, which is what a tangent line is supposed to do. So again, even though this isn't a proof of the power rule, we're seeing that the power rule does seem to work in this case because the tangent line it produced is a good one. All right, on to the next page. All right, we're going to go ahead and wrap things up with a couple more examples that illustrate a couple things we haven't seen yet, but they are things that can come up in the homework. And then we're going to look at one final definition in this section as well. All right, so first the examples. Find all values of x on the graph of f at which the tangent line is horizontal. All right, so a horizontal tangent line has a slope of 0. So we want to find places where the tangent line would have a slope of 0. That means we want to find places where the function would have a 0 derivative. So we jump in first thing and find the derivative. This function's all set up and ready to go in terms of derivative, this piece, this piece, this piece, or power rule, and then a constant. So we can jump in and just go. Bring that 3 out front, multiply with the 1/3, you would get a 1 times x to the power 1 less, which would be 2. The next one, bring that 2 down, multiply it with the 3, so we get minus 6x to the first, or just minus 6x. On the 5x, that's linear, so the coefficient is the derivative. You can use the power rule there, bring the 1 down, 1 times 5 is 5. X to the 0 is 1, so it works out the same, but you want to get used to that. If it's a linear term, you just get the coefficient, and the derivative of the constant term 10 is just a 0. So we end up with x squared minus 6x plus 5. And what we're curious about is when is the derivative equal to 0? So we take that derivative, x squared minus 6x plus 5. We set it equal to 0, and we try and figure out where does that happen. We do that by factoring. So we try and come up with two numbers that multiply to 5 and add up to negative 6. Minus 1 and minus 5 would get that job done. Negative 1 times negative 5 is plus 5, and add those two together, you get negative 6. So we come up with two solutions there, x equals 1 and x equals 5. And that's, if you go back and look at the directions that we were given, they just wanted us to find all the x values where the tangent is horizontal, so figuring out where the derivative is equal to 0 gets that job done, and so it's those two spots. All right, so let's try something very similar to that. Find all the values of x on the graph of f for which the slope of the curve is 7. Are we dealing with the exact same function? It looks like we are. So if we're dealing with the same function, we know that its derivative is x squared minus 6x plus 5. So should we factor that again? No, because we're not curious about when it's equal to 0 this time. We want to know where the slope of the curve has a tangent line of 7. So if we're looking for a spot where the slope of the curve is 7, meaning the slope of the tangent line is 7, then what we want to do is take this derivative and set it equal to 7. So x squared minus 6x plus 5 equals 7. And then in order to solve these quadratics, we got to get 0 on one side. So that becomes x squared minus 6x. Let's see, that'd be a minus 2 equals 0. So we'd like to factor that. To factor it, we'd want to try and find two numbers whose product is negative 2 and add up to negative 6. But to get that negative 2, that can only be a 2 and a 1. And if you want it to be negative 2, you'd put the negative on the bigger number, but then the sum is negative 1 instead of negative 6. So it looks like this does not factor. So you could plug it into the quadratic formula. It turns out, though, the messiest time to use the quadratic formula is when you have an even number right here. And if the coefficient out front is a 1, that's one of the easiest times ever to do something we don't do very often, which is the completing the square technique. So I'm going to do that because it's less messy than the quadratic formula. And it gets you a reminder of how completing the square works. So what I'm going to do first is move that 2 over to the other side. And I'm going to leave this blank spot right here. And we need to add a number in there to complete the square. The trick to that is to take the coefficient of x, -6, cut it in half, and square it. So that would be -3 squared, or 9. So we can complete the square by adding 9 to both sides. And then the proof that that did in fact work comes from the factoring. What are two numbers that multiply to 9 and add up to -6? It would be -3 and -3. And since both factors would be x minus 3, we get x minus 3 squared. On the other side, we get an 11. So what's good about this is we can just jump in right away and take a square root of both sides. So what does that give us? On the left, the square root and the square cancel, and we get x minus 3. And on the other side, we need to make sure we do plus or minus so that we get both solutions, not just one. And then add 3 to both sides, and we get x equals 3 plus or minus the square root of 11. So there would be the two x values that get the job done. So most of the time when they ask us to find a special spot on the curve based on slope, it's usually they want a horizontal tangent, so we look for where the derivative is 0. But they can ask us other things about the slope too, and we can then set the derivative equal to those values and still find them. All right, let's wrap things up with one final thing, which is the derivative, or the definition of the nth derivative. So for any positive integer n, the nth derivative of a function is obtained from the function by differentiating n times. So the nth derivative can be written a few different ways. So we have, this is the standard way, we would say the first derivative is f prime of x, and the second derivative is f double prime of x, and then we get f triple prime of x, and you could just keep going like that. But what we usually do is start writing what looks like an exponent, but it's really the number of derivatives we're going to take, so f4 of x, and so on, up to some nth derivative of x. So most of the time we just take a first derivative and a second derivative, but there are times later, especially in Math 2, where you will take the derivative over and over and over again. It's not hard to do, it just means that you got to repeat the work. You take the derivative and you get an answer, and then you take the derivative of that answer. So let's see what that looks like. Find the fourth derivative of this guy. So let's see, let's find the first derivative. So f prime of x would be bring the 10 down, multiply with the 5, so that's 50. Subtract 1 from the power, so that's a 9. Minus, bring the 5 down, multiply with the 6, that's 30. Subtract 1 from the power, that's 4. Next part is linear, so we just get the coefficient minus 27, and the derivative of the constant is 0. So there's our first derivative. And then you'd go on to take the second derivative by just taking the thing we just got the derivative of and taking the derivative again. So take the derivative of the 50, x to the 9th minus 30, x to the 4th minus 27. So derivative of the first term, you bring the 9 down, multiply with the 50, you get 450, x to the 8, subtracting 1 from the power. Bring the 4 down, multiply with the 30, and we get minus 120 x to the 3rd when we subtract 1 from that power. And the derivative of the 27 is 0. Then we go on to the third derivative. Third derivative would just be the derivative of the second derivative. So bring the 8 down times the 450, and that is 3,600 if you do the math on that. And x to the power 1 less, so subtract 1 from the 8, and you get a 7. Bring the 3 down, multiply with the 120, we get minus 360, x squared. So there's your first three derivatives. All right, let's finish this up by taking the fourth derivative. So the derivative of our previous answer in notation would be f4 of x We want the derivative of this first term, 3600 x to the 7th, so 7 times 3600 is 25,200. Subtract 1 from the power, you get x to the 6th. Bring that 2 down times the 360, you get minus 720, and x would now be to the first. So there's a first, second, third, and fourth derivative. It's just continuing the process where you take your previous answer and take the derivative again. Just a little bit about notation. So other ways you can write this nth derivative, or at least one other way, is you could say that you're taking the derivative n times of y with respect to x all n times. So that's one way to write an nth derivative. That's another. We don't really get into these nth derivative spots too often. The nth derivative is something we'll do more in Math 2 than in Math 1. Most of the time in Math 1, we're going to take a first derivative and a second, and then that'll be that. All right, that wraps up section 3.2.